In this video, we'll explore properties of functions. The first property we'll discuss is whether a function is even, odd, or neither. First, to check even or odd, we want to make sure that for every x value in the domain, its corresponding negative x also exists in the domain. Then we can check for even, we know we have y-axis symmetry, and for odd, we have origin symmetry. So let's look at two examples. If I look at my first one, I have a graph, and I can see that within that graph that all real numbers are working in my domain. Since that includes all real numbers, I know that for every positive x, it does have a corresponding negative x. Now I can check even or odd, and I see that there is y-axis symmetry. I could fold across the y-axis and see that it matches perfectly. That tells me this is an even function. In my second example, again, I see that the domain is all real numbers, so I can check even and odd. So I'm going to plug in this case, a negative x, because I don't have the graph, and see what happens. Now when I plug in negative x, this negative x cubed means that I can look at the negative quantity x cubed, and a negative times a negative makes a positive 2x cubed. So that means that when I plug a negative x into the function, it makes the function become the opposite. In other words, negative f of x. So f of negative x gives me negative f of x, and that right here is the definition of being odd. I could also have graphed this function if I want to double check as well, and I can see that that has symmetry through the origin by looking at the graph. Now if I wanted to determine whether a function is increasing, decreasing, and where it's staying constant, I'm going to actually use the graph, and I'm going to look at corresponding x values and see what happens to their f of x when that's plugged in. It's increasing if when my x values increase, the function increases. It's decreasing if as my x values increase, the function of those x's decrease. And it's constant if for all x values, the function of x is equal. We write them in notation, interval notation of the x values, so we're telling from this x to that x it's increasing, and so forth and so on. If we have multiple locations of increasing, decreasing, or constant, we list them all and we put the union in between them. So here's my graph. I typically read a graph going left to right and seeing what's going on and fill in the increasing, decreasing, and constant as I go. So if I look at this graph reading left to right, I see that I'm decreasing from 7 to 0. So I fill in decreasing from negative 7 to 0. And I use parentheses because we consider it an open interval. You can't be exactly on that point. If I look at the next part, I'm staying constant from 0 to 4. There's no increase, no decrease. It's constant. And then for the last part, I see from 4 to 7, the graph or the function is increasing. So from 4 to 7, I'd put increasing. Now the last aspect we'll look at is the idea of finding the maxima and minima within a graph. You have local and absolute maxima and local and absolute minima. With the local maxima, we're looking at intervals within the function where there's a specific value such that the function at that value is greater than all the other functions for all the other x values in that same interval. You can think about it as if there's a little hill in your graph, is the way I like to think about it. For the absolute maxima, it's going to be that absolute peak in the entire graph of the function. So that's the difference. Local minimum, you can have like little hills. Absolute maxima, we're going to have a peak of the entire graph. When we talk about the minima, it's the opposites. Think about it as valleys in our graph. So there exists some c value that when we take the function of it, it's less than all the other x values functions in that specific interval. Whereas the absolute minima is going to be the absolute lowest point on the graph of the function. Now, maxima and minima may not exist in a graph. When they're local, they may not exist if there exist no hills or no valleys within that graph for a c, or there may be a hole in our graph, a literal hole, a hollow dot at that specific point that would represent the max or the min. The absolute max and min may not exist if the graph continues to go increase or continues to decrease beyond all points, continuous graphs. Or if there was a hole at a specific location that would have been that absolute max or min as well. So here's an example. And I want you to find all the max and min in this graph if they exist. Well, for our local max, we're looking for any peaks that may exist, and what we can see is that there is a little hill right at 1/2, 3/4. So the way we would write that local max is that f of 1/2 equals 3/4. When we look at our local min, we're going to look and say, are there any small valleys in this? And these are just common terms I'm using to help explain, looking for those little dips, if you like. And we can see in this case that there's two different places where it occurs, and we need to list them both. So we would say f of -1 equals -3, and f of 1.6 equals -1.2. Now when we talk about the absolute max, we're looking for, is there an absolute peak to our graph? And in this case, if you look, our graph is going upward continuously. It never stops going upward. So there are no absolute maximum. Then when we talk about the absolute minimum, we're looking for, is there an absolute low point to our graph? If we look, there actually isn't a low point right here at -1, -3. So what we would say is that f of -1 equals -3. Not only is it a local minima, it's an absolute minimum as well.